22 million light-years from Earth in the constellation Cepheus. A single point of light was living on borrowed time. Astronomers cataloged it with a name that reads more like a coordinate than a star, N6946BH1. It burned inside the sprawling arms of the galaxy NGC 6946, and by every measure astronomers could take, it was enormous. Estimates placed its mass at roughly 25 times that of our Sun. That number carries a destiny. A star that heavy does not fade quietly into old age like a modest yellow dwarf. It races through its fuel, fusing hydrogen into helium, helium into carbon, carbon into oxygen, neon, silicon, and finally iron. Iron is the wall. When a massive core builds a heart of iron, fusion can no longer pay its own energy debt. The core collapses in less than a second, and the outer layers rebound in a titanic explosion. That explosion is a supernova. For decades, this was treated not as a possibility, but as a certainty. A star of 25 solar masses was supposed to end in one of the most violent events in the universe, a flash briefly outshining entire galaxies, seeding space with heavy elements. Textbooks drew the arrow plainly: big star, then brilliant death. When astronomers turned their instruments toward N6946BH1 in 2009, they were not expecting a mystery. They were expecting fireworks, sooner or later. They were watching a candle they believed must one day detonate. The star sat there, red and swollen, a supergiant already deep into the final chapters of its life. Everything about it fit the profile of a future supernova. The mass was right. The color was right. The stage of evolution was right. And yet the sky had a different ending in mind, one that no textbook diagram had prepared observers to see. What happened to N6946BH1 would not match the arrow. There would be no galaxy outshining flash, no expanding shell of debris, no triumphant announcement of a star's death. Instead, there would be a whisper, a dimming, and eventually a silence. But before we follow that silence, we must understand why astronomers were watching this particular galaxy at all. NGC 6946 has earned its nickname. Astronomers call it the Fireworks Galaxy, and the title is not marketing. It refers to a genuine, measurable record. Since the year 1917, observers have documented at least 10 supernovae erupting within this single spiral galaxy: SN1917A, SN1939C, SN1948b, SN1968d, SN1969P, SN1980K, SN2002HH, SN2004E, SN2008S, and SN2017EAW. No other galaxy in the nearby universe has offered up so many stellar explosions to human telescopes in roughly a century of watching. That density of catastrophe made NGC 6946 something of a natural laboratory. It sits about 22 million light-years away, close enough for large telescopes to resolve individual bright stars, yet far enough to fit its entire luminous disk within a single field of view. Its face tilts nearly toward us, so its spiral arms unwind like a pinwheel seen from above, studded with pink knots of star-forming gas and blue clusters of young, massive suns. Those massive suns are precisely the ones destined to explode. A galaxy churning out new stars at a furious rate also produces heavyweights that die fast and die loud. So NGC 6946 became a place worth returning to, again and again, with the Hubble Space Telescope, with ground-based surveys, with the infrared eyes of the Spitzer Space Telescope. If you wanted to catch stars in the act of dying, this was one of the best addresses in the sky. It was this reputation that drew the attention of researchers hunting for something unusual. A team began monitoring the galaxy's brightest supergiants, watching for the moment one of them would finally ignite into a supernova. They were essentially staking out the crime scene before the crime, cataloging the doomed candidates so that when one detonated, they would have a before and after record. N6946BH1 was one name on that watch list. It was bright, it was red, it was massive, and it fit the profile perfectly. What no one anticipated was that when the moment came, the star would not obey the script. In 2009, it did something faint and something wrong. In 2009, N6946BH1 flickered. For a star being watched as a future supernova, any brightening should have been the headline event, the beginning of the explosion astronomers had anticipated. But this brightening was wrong in a way that unsettled everyone who examined it. It was weak. A genuine core collapse supernova can shine with the light of billions of suns, briefly rivaling its entire host galaxy. What N6946BH1 produced was a modest, muted swelling of luminosity, an outburst that peaked at only about 1,000,000 times the sun's brightness before beginning to subside. In the vocabulary of stellar death, that is barely a murmur. It was far too faint to be the detonation the star's 25 solar masses had promised. The signal did not fit the category. It was not bright enough to be a supernova, yet it was clearly not the star behaving normally either. It sat in an uncomfortable middle ground, a transient event that resisted easy labeling. Some brightenings like this had been seen before and dismissed as stellar hiccups. Eruptions where a massive star sheds a shell of material without dying. But this one demanded closer scrutiny because of what followed. Among the astronomers paying attention was a team led by Christopher Kachanik at Ohio State University, researchers running a dedicated survey specifically designed to catch failed supernovae, stars that might collapse without exploding. They had been monitoring dozens of galaxies, comparing images year after year, searching for a massive star that simply disappeared. N6946BH1 moved onto their radar as an anomaly worth tracking, a candidate that had done something in 2009 that no ordinary supernova would do. The team began treating the star not as a routine variable, but as a possible example of the very phenomenon they were hunting. The plan was straightforward and patient. Keep watching. Return with Hubble. Return with Spitzer. Compare the frames across the years and see whether the star recovered its former brightness, as a surviving supergiant would, or whether it did something no living star should do. The 2009 flash was only the opening act. What mattered was what the star looked like afterward, in the images that came in the years that followed. The years after 2009 told a story no one had scripted. Astronomers pulled up the archived images and compared them frame by frame, epoch by epoch. In earlier Hubble Space Telescope observations, N6946BH1 was plainly there, a luminous red supergiant sitting exactly where the catalog said it should be, one bright point among the crowded stars of NGC 6946. After its faint 2009 outburst, the expectation, if it had merely erupted and survived, was recovery. A surviving supergiant should have brightened back up, resumed its place, returned to the roster of the living. It did not. Instead, across successive years, the star grew dimmer in visible light. Each new set of images showed less of it. By 2015, when Hubble again turned toward that patch of the galaxy, astronomers found something startling in the optical frames. Nothing. Where a brilliant red supergiant had shone for years, there was now an absence. The star had faded below the threshold of visible detection, and, to the eyes of the telescope tuned to visible wavelengths, simply vanished. This is not how massive stars are supposed to behave. Stars do not quietly wink out. They either continue burning, brightening, and dimming within known limits, or they die in a way that leaves an unmistakable signature, an explosion, an expanding shell of glowing debris, a supernova remnant. N6946BH1 offered none of that. There was no bright flash to mark a death, no lingering nebula of shredded stellar material. There was only a light that had steadily dimmed and then was gone from the visible sky. A suspicion began to take shape among the researchers, a suspicion that grew heavier with each empty frame. What if nothing had been left behind to shine? What if the star had not exploded and had not survived, but had instead disappeared into some object that emitted almost no visible light at all? A vanishing act on this scale hinted at something extraordinary, but visible light is only one window. Absence in the optical does not prove absence in every wavelength. To know whether the star was truly gone, astronomers needed to look where cooling matter still glows. They turned to the infrared. When a star disappears from visible light, the next question is whether it disappeared from everything. Visible wavelengths are only part of the spectrum. Cooler material too faint or too cold to shine in ordinary light, still radiates heat in the infrared. So astronomers turned to the Spitzer Space Telescope, an observatory built to see exactly that kind of warmth, the faint glow of objects far too dim for optical instruments. At the precise location where N6946BH1 had vanished, Spitzer found something. Not a star, not the sharp point of light that had shone before, but a faint infrared source, a warm smudge lingering where the supergiant used to be. Critically, it was fading. Follow-up observations showed the infrared glow diminishing over time, cooling and dimming rather than holding steady or brightening. The surviving star would keep pouring out energy. This source was doing the opposite, quietly bleeding away its warmth. The interpretation astronomers reached is one of the most evocative in modern stellar physics. When the star's core collapsed, the theory goes, it may have flung off only a thin outer envelope of material, a modest shell of gas that briefly produced the weak 2009 brightening. That ejected material then expanded and cooled. As it cooled, it stopped shining in visible light and instead radiated in the infrared, a dwindling afterglow of a death without a detonation. What was heating this fading shell? Possibly the last energy from the collapse, or matter falling inward and releasing heat as it was consumed. The infrared whisper was, in this reading, not the star itself, but the fading breath of its disappearance, the warmth of debris settling around whatever the star had become. It was consistent with a scenario in which no true supernova ever occurred, in which the star simply extinguished itself and left a cooling remnant behind. The signal was faint, ambiguous and precious. It was the difference between a star that had merely hidden and a star that had genuinely ended. That diminishing warmth pointed toward a fate long predicted in theory, but never confidently observed. A massive star collapsing directly into a black hole, without the fireworks. To understand what that means, we must confront the physics of the failed supernova. To understand what may have happened to N6946BH1, we must go inside a dying star. A star of roughly 25 solar masses burns through its fuel in a frantic hierarchy. Hydrogen fuses to helium, helium to carbon, carbon to oxygen, then neon, silicon, and finally iron. Each stage burns faster than the last. The final silicon burning phase, forging iron in the core, lasts barely a day. Iron is the endpoint. Fusing it consumes energy rather than releasing it, so the fire that has held the star up for millions of years suddenly fails. In the standard picture, the iron core collapses in less than a second, crushing to nuclear density and rebounding. A shockwave races outward, and neutrinos pour from the newborn neutron star, driving the outer layers off in a supernova. That is the fireworks the universe expects. But for the heaviest stars, the physics turns treacherous. When the core exceeds a critical mass, the rebound may stall. The shockwave, instead of tearing outward, chokes and falls back. Neutrinos alone cannot revive it. The proto-neutron star keeps gaining mass, passes the limit that any neutron star can bear, and collapses again, this time into a black hole. The explosion never escapes. This is the failed supernova. The star does not blow apart, it swallows itself. The outer envelope, hundreds of solar radii of hydrogen, is no longer held by any pressure from below. Much of it simply pours inward past the newborn event horizon, disappearing without light. Simulations by theorists suggest a signature, almost cruel in its subtlety. As the core collapses, it radiates away a small fraction of its mass in neutrinos, so quickly that the star's outer layers, no longer feeling the same gravity, gently lift and cool. The result is not a blast, but a faint brief glow, a shudder of a few 100,000 solar luminosities lasting months, followed by darkness. 25 solar masses lie in exactly the range where models predict this outcome becomes likely. N6946BH1 fit the theory almost perfectly. But if massive stars can vanish this way, one troubling question follows. Where, then, are all the supernovae we should be seeing? Astronomers have long kept a census of exploding stars, and the numbers do not add up. Across surveys, when researchers catalog the stars that erupt as core collapse supernovae, the progenitors they identify cluster at the lower end of the mass scale, typically between about 8 and 18 solar masses. The truly heavy stars, those above roughly 18 or 20 solar masses, are conspicuously scarce, yet we know these giants exist. We see them shining in nearby galaxies, blue and red supergiants of 25, 30, even 40 solar masses, blazing while they live. Something is happening to them at death. This discrepancy has a name, coined by Stephen Smart and others, who compiled the progenitor data, the red supergiant problem. If the heaviest supergiants explode as expected, we should routinely catch them in the act, matching a bright supernova to an archived image of the massive star that produced it. Instead, that matching almost never happens above the mysterious ceiling. Either the biggest stars shed enormous mass before dying, or they are not exploding at all. Failed supernovae offer an elegant resolution. If stars above a threshold collapse directly into black holes, releasing little or no visible light, then they would drop out of the supernova count precisely as observed. They would live loudly and die quietly, leaving the statistics skewed towards smaller stars. Theoretical estimates suggested that somewhere between 10 and 30% of core collapses might fail this way. Christopher Kachanik and his colleagues had launched a dedicated survey with exactly this question in mind, monitoring roughly 1 million supergiants across nearby galaxies, watching not for new lights but for old ones that simply switched off. N6946BH1 was the first strong catch. One vanished star among 1 million watched is not a coincidence to dismiss lightly. It was the physical instance the missing stars problem seemed to demand. A 25 solar mass supergiant that failed to explode and disappeared. The theory had predicted such objects. Here apparently was one. And yet, a single disappearance can be explained in more than one way. Not everyone was convinced the star was truly gone. Extraordinary claims invite scrutiny, and the disappearance of N6946BH1 was no exception. Skeptics raised several alternatives, each of which had to be confronted before the failed supernova interpretation could stand. The first was dust. Massive stars are prone to violent outbursts, ejecting shells of gas that condense into obscuring dust. Perhaps the star had not vanished at all, but wrapped itself in a cocoon, its light absorbed and re-radiated at wavelengths Hubble could not see. This is where the Spitzer infrared data became decisive but not conclusive. If dust were merely hiding a living star, the reprocessed infrared glow should have persisted at a roughly steady level. Instead, the mid-infrared signal continued to fade year after year, consistent with a source that was genuinely diming, not one merely veiled. Yet dust models are flexible, and some argued the fading could still be accommodated. A second possibility was a survivor. Perhaps what astronomers had watched was a great eruption, akin to the 19th century outburst of Eta Carinae, which brightened enormously and then dimmed while the star endured. In this scenario, N6946BH1 might still be there, temporarily faint, destined to reappear. Repeated deep imaging in later years searched for exactly such a rebound. The star did not return to its former brightness, weakening the survivor case, though the possibility of a deeply enshrouded remnant could not be entirely dismissed. A third objection concerned the source itself. Some questioned whether the pre-2009 object was truly a single 25 solar mass star or a blend of light from several stars in a crowded 22 million light-year distant field. If so, the vanishing might reflect the fading of one component amid a cluster. Careful photometry addressed this, but the resolution limits at such a distance leave room for argument. Each alternative could be weakened. None could be absolutely eliminated. The evidence pointed strongly toward direct collapse, but pointing is not proving. What remained was a case built on convergence, a fading star, a dwindling infrared whisper, a mass in the predicted range, and no returning light. Strong, coherent, compelling, and still, honestly, incomplete. So where does this leave N6946BH1? Not as proof, but as the strongest single instance yet found of a star that may have collapsed into a black hole without exploding. The word candidate matters. Science does not close a case on one object seen at 22 million light-years, no matter how well the pieces fit. And here, remarkably, the pieces do fit. A red supergiant of roughly 25 solar masses, sitting squarely in the mass range where models predict direct collapse becomes likely. A brief, weak brightening in 2009, consistent with the gentle shudder simulations describe, rather than a supernova's blast. A steady fading from visible light through Hubble's eyes until, by 2015, nothing remained where a bright supergiant had shone. And a diminishing infrared glow mapped by Spitzer, behaving like cooling debris rather than a hidden survivor. Each strand alone could be explained away. Together, they form a coherent story that no competing explanation matches as cleanly. The alternatives, dust, eruption, blended sources, remain logically possible, and honest researchers keep them on the table. That is not weakness. It is how the discipline guards itself. Future instruments may resolve the ambiguity. The James Webb Space Telescope can probe the site in infrared with far greater sensitivity, searching for any lingering star or confirming the source is truly gone. Continued monitoring of nearby galaxies may catch more disappearances, turning a single anomaly into a population. If failed supernovae occur as often as theory suggests, others will be found, and N6946BH1 will be remembered as the first clear glimpse. For now it stands alone at the frontier, a specific point of light in a specific spiral galaxy that behaved as if a star had quietly ceased to be. Christopher Kochnick and his colleagues gave us not certainty but the best evidence yet that some giants end not in fire but in a silent surrender to gravity. We watched a star of 25 solar masses brighten faintly, then fade, then vanish, leaving only a cooling ember and a black hole where a sun once burned. And so, the conclusion, still tentative, still testable, endures with quiet weight. A star may have died in silence.